Let's work on a problem. I've got a box here. Let's give it a mass. Let's give it a mass equaling, let's say, 10 kilograms. Keep numbers nice and simple. And I'm going to apply a force. And the force I'm going to apply to that box is, just again to keep everything nice and simple, 10 newtons. And I'm going to apply it for distance, and this time let's shake up our numbers a little bit, for 50 meters. Now, if we graph out that force over 50 meters, well, our force stays the same over the course of that 50 meters. So let's put that on here. It's not exactly level. That's okay, that'll work. That force will stay constant for that 50 meters. And then what's going to happen at point 2 here, at this blue 2, our force is going to stop. We're going to stop pushing it at this point. So let's define that. Force is just suddenly going to drop off. And then no more force. So when I'm applying that force, I'm applying work into this system. I'm putting work into this system. And as I apply that force over this distance, the area under this curve will be equivalent to the force times the distance. If you remember when we looked at our basic idea of an integral. This would be just a general shape, just a rectangle, and the area under that curve is just going to be the base, which is my distance, times my height, which is my force. And so the work I do on this system is going to be equal to 10, the force of 10, times the distance of 50. 10 times 50 is 500 joules. So when I do that work, I now have 500 joules in my system. So by point number 2, I have 500 joules of energy in this system. Now until that box does work on something else, that energy stays in that system. So from this point onwards, between 2 and 3, we have a total of 500 joules in my system, in that box. That's what I'm defining as my system. The box is the system. So now, let's look at how that energy is changing forms. And to do this, I want to take a look at an energy versus distance graph. So that would be if we took this graph and we graphed the area under this curve. If we did that, well, as I continue onwards, the area under this curve is going to be continuing to increase. And so when we have that increasing, what we say is the mechanical energy. That's really the physical energy, as opposed to like electrical energy or chemical energy. That mechanical energy is going to go up. In physics, we're going to be dealing almost exclusively with mechanical energy. And so let's say this point right here, this is our number 2 point. Let's say right here is 500 joules. And so from 0 to 500, I'm going to be increasing as I continue to apply that force. And so as we push that box, let's see if I can line this up well. That's about right. As we continue to push this box, I will have an even slope. An even slope here of my mechanical energy going up. After this point, I no longer apply that force. And so my total mechanical energy, that's almost perfect. Almost. My total mechanical energy will stay the same for the rest of this time. But what about my kinetic energy and potential energy? Well, since I'm pushing this box on a flat surface, I'm applying a net force to it. Well, it's going to be accelerating. It's going to be steadily increasing in velocity. And I want to know, what is my velocity going to be at point number 2? So let's first graph this as well so we can continue getting a good idea of what this is going to look like. I'm going to line my ruler back up. Let's see if I can do this. And at the same time that my mechanical energy is going up, what type of mechanical energy is that going to be? Because mechanical energy is just a way to say this is not stored in a chemical bond and it's not moving charges like electrons. It's not electrical. This is going to be physical. It's going to be physical mechanical energy. It's going to be dealing with forces and stuff. Well, that's going to be in the form of kinetic energy. So mechanical energy is the total energy in our system. But kinetic energy is the specific form that that energy is taking place in as I apply that force. And so let's graph that as well. As I go this way, as I continue on this path, my kinetic energy is going up. So that's my kinetic energy increasing. And at this point, I'm going to have 500 joules of kinetic energy. Do I have any potential energy? Well, if I look at this again, I'm at a flat level surface. As I'm moving along, I'm flat. After point 2, I start to increase my height. So before point 2, my kinetic energy is going to be 0. Or I'm sorry, my potential energy is going to be 0. And my kinetic energy will be greater than 0. It'll be steadily going up between 0 and 500. By the time it reaches point 2, this will equal 500 joules. But between point 1 and point 2, it is steadily increasing. And so if I have 500 joules of kinetic energy, what's that velocity going to be? It's going to be 500 joules equals 1/2 mv squared. So I'm going to take 500, I'm going to multiply it by 2, times 2 equals mv squared, and then that'll be 1,000 divided by my mass, which is we defined as 10 kilograms, equals v squared. And when I do that, I get 100 equals v squared, square root of both sides, and the square root of 100 is 10. So I get 10 meters per second at point 2 right here. So right here, my velocity is 10 meters per second. But then I hit this slope. And when I go up this slope, I'm converting from that kinetic energy into potential energy. But I'm not doing any work. We're going to assume that this is frictionless. There's no friction here. So all of that energy is just going into potential energy until I reach a maximum height. At that maximum height, all of my kinetic energy will have converted into potential energy. So this is how we track these energy changes. So between points 2 and 3, let's write these down here. This is point 2, this is point 3, all the way over on the end. Between points 2 and 3, my kinetic energy begins to go down. I'm going to slow down as I go up this slope. And I'm going to slow down at a linear pace. So let's put this straight edge up here. And so my kinetic energy goes down. But notice, my total mechanical energy is still up. It stays the same. So my kinetic energy goes down, but my mechanical energy stays up. So what's going to happen is my potential energy will be moving up at an equivalent rate. So between point 1 and point 2, my potential energy is 0. We're on a flat level surface. Potential energy is 0. But then, almost perfect. Get better at this. But then, between points 2 and 3, my potential energy goes up until it hits the maximum mechanical energy. Right here is where my potential energy equals my mechanical energy, which means there's no energy left to be in the form of kinetic energy, so kinetic energy is 0. What that means is my velocity must be 0. So we can calculate the height at this point by saying, well, since I've still got a total of 500 joules of mechanical energy in this system, all of that is going to get converted into potential energy. So right here, I've got 500 equals mgh. So I can just take 500 divided by mg, which is going to be 10 times 9.8 equals h. And when I do that calculation, I get a height of 5.1 meters. And so a velocity of 10 meters per second gets converted into a height of 5.1 meters. At this point, velocity equals 0, height equals 5.1. There we go. There's our first motion problem using energy.